Swayam Prabha. Digital India. Educated India.
Okay, good morning. In this lecture, I'll be discussing about bio-based conventional plastics. To get the context, so I'm kind of summarizing all the polymers, types of polymers we have discussed so far. Okay, so on the top left quadrant, we have conventional plastics that are fossil fuel based or petroleum based: polystyrene, polyvinyl chloride, polyethylene, polypropylene, PET. Okay, we know their applications. It's a commodity plastics, okay, available in large quantities, and many products are formed through these conventional polymers. Okay, and we also know what are the issues with these polymers. Okay, end of life issues, microplastic issues, health and environmental concerns. Okay, those are the limiting factors of these commodity polymers. And what we are saying is, can we replace these polymers with natural biopolymers? Then we are talking about this quadrant, where we were talking about various kinds of bio-based or bio-sourced polymers: cellulose, starch, pectin, agar, chitin, chitosan, etc. Okay, these polymers are already there in the nature. All we have to do is to purify them, extract them, and then see if we can use it for applications in which we want to remove the conventional plastics from. Okay, cellulose, polyhydroxyalkonates, PLA. Okay, so this is one sect. Okay, so these are the two domains. One which is commercially available, large scale, low cost, large scale availability, finding a lot of application, but having health risk and end of life issues. On the other hand, we have naturally available polymers, abundantly available, not harmful, but in terms of properties, they don't actually meet the functional requirements of commodity plastics. Okay, so then we also have another segment where we make use of the monomers chemicals from the fossil fuel, but build a molecule that would be biodegradable. Examples are the EcoFlex, EcoVI I was talking about in last class, which is nothing but polybutylene coadipate terephthalate, polyvinyl alcohol, polybutylene succinate. So these are all fossil fuel derived polymers, yet they can actually biocompostable. They are biodegradable. Okay, they are not going to be as harmful as these ones. Okay, so we have seen these three. So now we are going to another possibility where we want to basically build the same conventional plastics, but draw the monomers from natural sources. Okay, so here we have monomers from fossil fuel or petroleum, and these polymers are non-degradable. Here we have monomers and polymers derived from natural sources but biodegradable. So here we have monomers, chemicals derived from fossil fuel, but the polymers are actually compostable. Okay, so now we are coming to this particular segment where we want to build the same conventional polymers like polyethylene, polystyrene, PET, right, polyamides, polyurethanes, but the raw material should come from nature. Okay, and that's what the context of this lecture is going to be. So why we need to look at this is because there is an increasing trend in the production of bio-based polymers. Okay, so if you see here, we have this biodegradable polymers, and this is bio-based non-biodegradable. Okay, what that means? Bio-based non-biodegradable means these ones. So these are bio-based, but they are non-degradable as much as this conventional plastics are. So what is the unique, what are the advantage of going from here to here? Well, we don't depend on fossil fuel anymore. We can draw the raw material from the natural sources and build a molecule, but still we have the same end of life issue of degradation, microplastic pollution, everything. Okay, so that's what this green here means. Bio-based non-biodegradable polymers are polymers which are whose monomers are derived from natural sources, but the end polymer is like a conventional polymer that's non-degradable. Okay, because structurally, chemical structure wise the same, but the raw materials are coming from bio sources. Then we have this segment which is called biodegradable, which could mean either this or this, because they are end of life. From an end of life point of view, they are biodegradable regardless of what is the origin, whether it is a fossil fuel based or whether it's from nature based. Okay, so now if you look at year 2020 and 2021, you see that the biodegradable polymers production is about, this is given in terms of thousands of tons, so you could say about 1.2 million tons, and then it goes a little bit up about 1.5 million tons of biodegradable plastics. And if you look at the bio-based non-degradable, that is pretty much same between 20 and 21, but then there is a forecast being given till 2026. You can see that the increasing trend in case of both bio-based non-biodegradable as well as biodegradable. Okay, so there is a market push towards these kind of biodegradable, either biodegradable polymers or bio-based non-biodegradable polymers, both ways. Okay, that's going to be an increasing trend. Especially the increase is actually more in the case of biodegradable, as you can see. So here also we are comparing between among these biodegradable polymers from 2021 to 2026, the forecast has been also projected. If you see as of 2021, the data which was published then, you see that the majority of these polymers are actually PBAT and PLA. Both of them having about roughly 19% of the total biopolymer production. This is not the total plastic, it's only in the biodegradable segment. About 20% is PBAT and PLA each. Then there are other things. For example, PBS has only about 3.5%, PHA is very low, it's less than 2%. Starch is quite high, it's about 16% because TPS, starch based products we see. Cellulose films are very less, right? And then on the left hand side, if you see, these are all bio-based non-biodegradable. That means these are all conventional plastics, but the raw materials are drawn from nature. Polyethylene, PET, polyamide, polypropylene, etc. So you can see that only polyethylene has about 9.5%, PET 6.2%, polyamide about 9.1%. Okay, so this is the status of 2021. Now what has been projected in 2022, if you see, a big push has happened in PBS. Okay, the PBS production can probably go from a ratio of 3.5% to 16%. Okay, and you can also see the total amount of bioplastic put together, both bio-based and non-biodegradable as well as biodegradable put together, we expect from 2.42 million to about 7.59 million. About 3 to 4 folds increase in the total quantity of bioplastic is going to be increased. In that increase, the proportions are now changing. We are going to see more and more production of PBS in the market coming up. PBAT and PLA will still have the market share, and then you see that the polyamide also is seem to be going to be increased from 9 to 15%. Okay, so so both bio-based and non-biodegradable is upcoming, and then this fossil fuel based but biodegradable polymers like PBS is also something on the rise. Okay. You can actually look at this report, Plastics Europe 2021, to look at more of this in terms of application, what increase going to happen, all that you can see from there. So now I want to just skim through few examples of what is this called bio-based conventional plastics, starting from bio-based polyethylene. In short, it's called bio-PE. So bio-PE is nothing but polyethylene molecule, the same CH2, 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 but the monomer ethylene is not taken from the crude oil distillation, but it is taken from bio sources. Okay, so the end molecule bio-PE would have a very similar chemical structure of that of the conventional polyethylene, but only thing is the source, the monomer source is different. Okay, so as of now, Dow Chemical and a Brazilian based company Braskem, both of them are producing bio polyethylene in the market. Okay, so the way they do that is they go to the agriculture products like sugar cane, sugar beet, starch, lignocellulosic material. Okay, do all kinds of mechanical cleaning, washing, cutting and all that, and then they convert this sugar into glucose, sucrose juice, like how we make sugarcane juice. Okay, and then this is sent to a anaerobic fermenter, and this fermenter will make bioethanol. Okay, so bioethanol, as you know, is an upcoming area even for fuel consumption also. So we are now blending about 20% of ethanol in petrol. So that ethanol is coming actually from sugarcane, sugar industry. Okay, so now part of this bioethanol can go to fuel, the other part actually can go to making plastics also. Okay, so here what happens is this bioethanol is actually is purified by a distillation, and it basically gives some sort of mixture of ethanol and vinasse, and this is further purified via dehydration. So from ethanol you go to what is called ethylene. Okay, so ethanol is this CH3 CH2OH. Okay, so you have to do dehydration to go into an ethylene molecule like this, and ethylene is a monomer for polyethylene. Once you have this bioethylene, then you can do a free radical polymerization, right, and then you can get biopolyethylene or bio-PE. Note that ethylene is not a monomer only for polyethylene. It is also used for other polymers. For example, polystyrene. In polystyrene, you need styrene plus ethylene, and if you want to do polyvinyl chloride, also you need. Okay, so ethylene is going to be a monomer for many other polymers also. Okay, so polyethylene, polyvinyl chloride, polystyrene, etc., polyvinyl urethane, all that is going to be useful. Okay. Now with the biopolyethylene, you can also build high density, low density, linear low density polyethylene also. In the case of high density polyethylene, it's pretty much like a linear polyethylene chain, but then there is going to be a small amount of branches, ethylene branches distributed sporadically on the backbone. Okay, that will give you high density polyethylene. If you make this branching little bit more high density, you get linear low density polyethylene, and then if you graft higher molecular weight olefins like butadiene or hexene or pentene, then you get little longer side group that will give you low density polyethylene. So whatever is possible with fossil fuel based polyethylene, the same kind of molecular structure can be obtained through biopolyethylene process also, right. So here a comparison is being made between a petroleum based HDPE and the biopolyethylene, which is also HDPE from this company Braskem. Okay, so this is bio-PE, this is just a PE, conventional PE. Okay, so you can see that densities are very close because the molecular structures are very close. There is quite a bit of a difference in the melt flow index. Okay, and tensile modulus, there is a little bit of difference. Tensile strength is similar. Elongation at break also is very similar. And then they also did LC analysis for the polyethylene and then compared with the conventional polyethylene, and it's been shown that the bio-based polyethylene energy consumption is only about 10 megajoules for some base units, whereas the same amount of polyethylene if you were to create from petrol based is going to increase by about 85%, leading to 65 millijoules. Similarly, if you look at the greenhouse gas emission, the bio-based polyethylene would actually absorb CO2 because that CO2 is used from the plant to make sugar, whereas in the case of petroleum, it's only going to be released. So the bio-based polyethylene can be a good source, a good sink for CO2 management also. Okay, so therefore, by moving towards bio-based polymers, we are not only become less dependent on the petroleum based products, but also we can manage the CO2 in the ambient conditions also. Okay, so that's two important data. So now, as with any other polymer, biopolyethylene is also made as a composite with the others. For example, this bio-PE is mixed with PTT. Okay, so PTT is nothing but polytrimethyl terephthalate, and similarly bio-PE is mixed with PLA and natural fibers such as wood, cellulose powder, kenaf fibers, and then microparticles of volcanic powders, the tough fillers. Okay, so as much as we do with any other polymer, with the biopolyethylene, you can also add fillers, blend with other polymers to improve the strength and mechanical property and other things. Right. So this is about PE. Now the next polyolefin that is bio-based is biopolypropylene. As of now, there is no commercial production of biopolyethylene yet, but it is all mostly in the R&D and pilot scale. So here again, you start with this, starch, sugarcane bagasse, sugarcane juice, and then you convert them into a sucrose, glucose, sugars, and you do fermentation. In this case, the fermentation has to lead to isobutanol. In the previous case, we saw that glucose was fermented to become ethanol. Okay, so now by changing the strain, by changing the condition, you can direct the biochemical pathway such a way that glucose is consumed and isobutanol is produced. Once you have isobutanol, you can dehydrate it and then make biobutylene, and then through some other catalytic and intermediate process, you can actually make propylene, and from propylene to biopropylene. That's what we call as bio-PP. As I said, this is not yet commercially produced yet. Okay, most of them are in R&D state. So this is one pathway where we take sugar and then convert into glucose, and then in this way. There are other methods that are proposed in the literature, starting with methanol, convert them into butylene, and then from butylene to propylene, and from propylene to polypropylene. So this is one particular pathway. And there are other situations where you start with the glucose, convert them into acetone or 1,2 propane diol, and then this is converted into 2-propanol, from 2-propanol to propylene, and propylene to polypropylene. So as you can see here, multiple pathways are invented or discovered to make it low cost and high purity and high yield product, but still most of them are in the research pathways. So bio-PET, as I said before, bio-PE and bio-PET, these are the highly available bio-based non-biodegradable polymers. So in the case of PET, you need two monomers. One is ethylene glycol or EG, ethylene glycol, and then you have this terephthalic acid. You need two monomers. Both of these monomers can be obtained from natural sources, especially again from glucose. Glucose is obtained from sugar. Okay. So in the first pathway, glucose is fermented to become a bioethanol, like in the case of bio-PE, and then it is dehydrated into bioethylene. Then the bioethylene is oxidized. Instead of directly polymerizing into polyethylene, the bioethylene is oxidized to get ethylene glycol, which is nothing but this. Okay, CH2OH and CH2OH. This is bioethylene glycol. And similarly, the other one, terephthalic acid, can also be produced. Start with the glucose, make bioethanol, dehydrate to make it bioethylene, and then this is oxidized through various catalytic conversion into bioethylene glycol sugar, and this is converted into paraxylene, and then from paraxylene you get PTA. Okay, so this basically combines two methodology. One is a fermentation, another one is a chemical catalytic conversion of the raw material into some desired product. So what is missing in this flow chart is the details of fermentation conditions and chemical reaction conditions, such as ligands, catalysts, and reaction conditions. Okay. But there are methods that have been proven to work this way, that you can get polyethylene, ethylene glycol as well as terephthalic acid from glucose. Okay, so both monomers are from sugar. So if you go a little beyond, there are more research on getting the terephthalic acid not only from glucose but also from so many other molecules. Okay, for example, from isobutanol through catalytic conversion you can get PTA, or you can take this muconic acid, you can convert into PTA, or you can start with isoprene, sorbic acid, dimethyl furfural, 2-hydroxymethyl furfural, and then limonene. So these are all bunch of molecules that can be obtained through pyrolysis of biomass. Okay, you take wood or you take any other biomass based material, through some sort of a catalytic pyrolysis process, you can get these raw materials. Once you have these raw materials, you can also get terephthalic acid. That means the number of ways in which you can convert a natural product into a terephthalic acid are plenty. Okay, so So here this table, I don't know if you can read this. So what is being shown here is, I have shown only polyethylene terephthalate PET, and polyethylene terephthalate is a kind of an polyester. You can actually think about many other esters. For example, this PTT is polytrimethylene terephthalate, PBT is polybutylene terephthalate, PBS is polybutylene succinate, which is also an aliphatic ester. Then we have this polyethylene furan dicarboxylate, which is also an ester, and then polylactic acid, which is also an ester. So all these esters could actually in principle be obtained from natural sources. Okay, so these are the conditions that has been said, who is producing what and how much. Okay? This slide I will share with you a lot of details about who is making, what are the status of these productions. Some are in R&D, some are in commercial. Okay, so pretty much any polyester that you want to make, there is a bio-based method with which we can derive them. So then we have this bio-based polyamide. Polyamide basically means a nylon 6,6 or nylon 6, those kind of high performance materials. So here again you can see it is possible to make polyamide 6,6, nylon 6,6, or polyamide 4,6, polyamide 4,10, 6,10, 10,10 and 11. If you remember, this two numbers basically means that polyamides are actually built with the two monomers. Okay, so there is diamine and there is this diacid. Okay, there are two molecules. So depending upon the number of carbon chain in the diacid, in the diamine, you can give this number. In the case of PA66, we use this hexadiamine and adipic acid, both of them having 6 carbon each. Okay, that's why it's 4,6. Whereas if you look at this PF4,6, the butadiene, the amine will have only 4 carbons, but adipic acid will have 6, so 4,6, like that. Okay, depending upon the number of carbon units between the repeating units, you call them as PA6s or PA46. Traditionally, polyamides are manufactured from the fossil fuel based monomers, the hexamethyl diamine, hexene diamine, adipic acid. These are all from fossil fuel based. Okay, but you can also use oil and biomass like sugar, starch, lignocellulose, and then through various fermentation and chemical conversion, you can convert them into these raw material and then build polyamides. Okay, so you can see that there are fermentation steps and there are many oxidation steps, chemical conversion steps, with which we can convert the natural raw materials into the required monomers. Okay, and then you can do polycondensation and get all these polyamides. Then the next one is biopolyurethane. Biopolyurethane requires diols or polyols, and then so here again you can see that you can start with the oil, sugar and biomass, and you can actually get the isocyanates, and this NOP means natural polyols. Okay, and this BDO means butadiene diol. So you can use all this fermentation process and then chemical process to make the respective monomers, and once you have the monomers like polyols and BDOs, then that can be formed to make polyurethanes. Again, there are flow charts to make a polyvinyl alcohol as polyvinyl alcohol. Again, start with your biomass, convert them into through some fermentation with the yeast, make them into ethanol, from ethanol to ethylene, acetic acid, and then you get vinyl acetate. Okay, so for polyvinyl acetate, you need ethylene and acetic acid. Both of them are actually obtained from bioethanol, and ethanol is obtained from sugar, and sugar is obtained from biomass. Okay, and then there are also process in which you can actually make polystyrene, polyacrylic amide, and polymethyl methacrylate, which are all conventional polymers. but most of them are in the R&D. You can see R&D and pilot scale plant only. Okay, so this is a very fertile research field if you want to jump into. If you are a good chemist and if you know how to do fermentation, there's a whole lot of opportunity to make the required raw material for conventional plastics. You can see that polystyrene, PA, PMA is all potentially possible. And even rubber is also now looked upon by bio-based sources. So here we are talking about polyisoprene or isoprene rubber, or polybutylene isobutylene rubber, or polybutadiene. These are all elastomers, okay, something that is stretchable. So here again you need isoprene to make polyisoprene, and this isoprene is actually now obtained from fermentation of sugar. Okay, so you can see that again we are going back to starch based biomass, and through proper fermentation we can make this isoprene, from isoprene to polyisoprene. And then there is another process which is commercially available, is to ferment them into an isobutanol. From isobutanol you dehydrate and then you get isobutylene. From here you can get isobutyl rubber. Okay, this is commercially available. There are a few more which are actually in pilot scale. So you get this butadiene from fermentation product, and from here you can get butadiene rubber also. Okay, so okay, so that's all I'd like to say. So the point I'm trying to make is, if I go back here, the first slide, yeah. So in the first slide, this is probably the kind of take home message from this course. Okay, what are the kind of polymer that are there, and what are the sources and end of life. Okay, so on the left hand side top we have petroleum based monomer, non biodegradable polymer, but that have met our functional structural requirements and low cost. Okay, so that is what the current situation is. And what is available right now are these biopolymers, which are naturally available from various bio sources, marine sources, plant sources, animal sources, etc. But their properties are not as good as the conventional plastics. Okay, unless you make some reinforcement or blend with other polymers, they are not that good. So the other two choices are these two. One is you build the biodegradable molecules starting from fossil fuel based material. So that would be biodegradable, this would be biodegradable but fossil fuel based monomers. Okay, so now what we are talking about is this case where we draw the monomers and build the conventional plastics. Okay, so as much as this fossil fuel based polymers, the bio based polymers also going to be non degradable, but it reduces the dependence on the fossil fuel for monomer production. Okay, so that's a thing, and this is the upcoming area. So this we have known for a long time. Okay, if you look at the work started about starch and cellulose, it goes back to 1940s and 50s. People have worked on. Okay, it's a very old area, but this is an upcoming area because this is very difficult to do. How do I take my same source of sugar? How can I engineer my fermentation and catalytic process to drive the reaction towards one particular product, and that product is not going to be give you 100% purity. So there's going to be a lot of issues in separation and controlling the yield, right? And then if you succeed in there, then you can pretty much build all the conventional polymer from natural sources, right? So, and one important aspect of doing bio-based is this, that compared to the petroleum based, the bio-based polymers have a negative impact on the CO2. Okay, they don't release CO2, but they absorb CO2. The amount of energy required also goes down. Okay, so these are the unique selling points about bio-based polymers, but not biodegradable. Okay, so hope you understand the bio-based and biodegradable mean. Bio-based means the raw material is drawn from natural sources. Biodegradable or not degradable is related to the end of life approach. After use, whether it's going to degrade or not degrade. So the two phrases mean, one is source, bio-based or bio-based or petroleum based is to do the source of the raw material. Biodegradable or non-biodegradable means with regard to the end of life. Now you have all combinations. Okay, so you'll have 4 combinations. You'll have bio-based, non-biodegradable, bio-based, biodegradable. These are two sets. Then you have fossil fuel petroleum based, biodegradable, and petroleum based non-biodegradable. So these are the 4 classes, and that's what I showed in the first slide. Okay, so that's all. So I will share this slide and you can look at all these details I have shared here. Yeah.